In this video, we consider model selection in ARMA models. We work with the general ARMA PQ model, which is given by yt equal to a constant term plus theta 1 yt minus 1 plus all the way up to theta p yt minus p. So these are the autoregressive components. We have p lags of yt itself. Then we have epsilon t, our innovation, and then we have the moving average part alpha 1 epsilon t minus 1 all the way to alpha q epsilon t minus q. We note that t is equal to 1, 2, all the way to capital T. We note that the initial values are given. And finally, we make a distributional assumption about epsilon t. We assume here that it is normally distributed, and it's IID with mean 0 and variance sigma square. So we can use this assumption to estimate the model by maximum likelihood. In this video, we consider how to do model selection in an ARMA PQ model. We will use a simpler model, an ARMA 2.2 model, to illustrate and discuss how we can use first a general to specific approach to the model selection process, and second, how we can use the information criteria to select between non-nested models. So let's consider an example, an ARMA 2.2 model. So an ARMA 2.2 model is given by yt equal to a constant term, then we have two lags of yt, then we have epsilon t, and we have two moving average terms like this. We could use a general to specific approach. There we start with a general model. Let's assume that that's our ARMA 2.2 model. And then we start from that and impose restrictions on each of the parameters until we get as simple as possible a model. With the general to specific approach, it's important that we start with P and Q, that's the number of autoregressive and moving average components, high enough to get a well-specified model. In practice, that means at least a model with no autocorrelation in the estimated residuals. Alternatively, we can select P and Q by what is called Box-Jenkins identification, which is based on the idea that an MAQ process will have exactly Q non-zero elements in the autocorrelation function. Likewise, an ARP process will have exactly P non-zero terms in the partial autocorrelation function. So we can look at the autocorrelation function and the partial autocorrelation function that we estimate for the data we are working with, and we can look at how many terms are significant, and that we can use as a starting point to select the number P and Q. But just note that the Box-Jenkins identification approach is not very precise, and it's much better to make sure that we start with a well-specified model. So use the autocorrelation function and the partial autocorrelation function as a guide, but make sure that we start with enough lags to get a dynamically complete model, in particular a model with no autocorrelation in the estimated residuals. In the example, we assume now that the ARMA 2.2 model is indeed a well-specified model. Now, the second step of the general to specific approach is to test restrictions and remove insignificant terms in order to get a simpler model. So we impose restrictions on insignificant coefficients, and we end up with a specific model which is simpler than the one we started with and only has significant terms left. So that's the idea of the general to specific approach. Just note that if we had the ARMA 2.2 model, we could consider instead an ARMA 2.1 model. That's one restriction we could impose on the model. We would have a new model given by yt equal to the constant term. Then we have the two autoregressive components, epsilon t plus alpha 1 epsilon t minus 1. So we could go from the ARMA 2.2 model to an ARMA 2.1 model, and we could simply test this as the restriction that alpha 2 is equal to 0. Note that after, say that we accept that, then we could continue and we could consider, for example, an AR2 model, which is given by yt equal to constant term. We have the two autoregressive components, And then finally we have an epsilon t. So there's no moving average component here. Again, we could test this as the null, that now alpha 1 is equal to 0. So when we test restrictions, one way to do that is by simply using a t-test on individual coefficients. It is typically suggested that you start by removing the most insignificant coefficient, you get rid of that variable, then you re-estimate the model, and you continue that process. So note that when we do the t-test here, we're doing sequential testing. And we are testing sequentially nested models only. We could also consider, for example, the restriction taking us directly from an ARMA 2-2 model to an AR2 model. We could test that by the null, that alpha 1 is equal to alpha 2 equal to 0, and we could test that by a likelihood ratio test against the general model that we started with. So these are two different tests. One is a sequential testing procedure. The other here is a test directly from the general model to the AR2 model. Just note that there are many other paths we could have taken. We could have started by looking instead at an ARMA, say 1-2 model. That would correspond to testing the hypothesis that theta 2 is equal to 0. And after that, we could go and take a look at an ARMA, say 1-1 model, or we could look at an MA2 model. So there is a full nesting structure that we have not outlined here, but that just means that there's a lot of different paths we could have taken. And depending on where we start, we might end up with different models that are not rejected, which are not nested. So for example here, there's no way we can test the AR2 model against an ARMA 1-2 because we cannot impose a restriction on one of those and get the other model. In addition to the general to specific approach, we could do model selection based on information criteria. So there are different information criteria, but they are all of the same form. The information criteria is given by the log of the estimated residual variance plus a penalty term which depends on the sample size and the number of parameters in the model. So note that if we add more parameters, the residual variance will always decrease. So what we're doing with the information criteria is we are balancing the fit of the model and simplicity of the model. So for example, assume that we have estimated two models where we get the same estimated residual variance, but one of the models has a lot more parameters in it than the other one. Then we would choose the model with less parameters, the simpler model. So that's the idea of the information criteria. We simply select the model with the lowest information criteria. There's a number of different information criteria. They all differ in the way they define the penalty here. But three important examples, that's the Akaike, the Hannan-Quinn, and then the Schwartz-Bayesian criteria, the AIC, the HQ, and the BIC information criteria. These are reported by most software packages. Note that we can use this to select between non-nested models. For example here, we could use this to test an ARMA 1-2 model against an AR2 model. So here we could use the information criteria that we could not test using a general to specific approach, but in the end we could look at all the nth paths, so to speak, that we get from a general to specific approach, and we could choose between them based on the information criteria. So that's all for now. Thanks for watching.